Anyways, let's go ahead and get started. Doesn't look like anybody has posted any questions other than the one I already answered. I did ask everyone to go ahead and chat me your first and last name. It looks like most of you have done that. We are going, as I said, into chapter 26, and chapter 26 is called DC circuits, meaning direct current circuits. The first section's on electromotive force and terminal voltage. The second section's on resistors in series and parallel. I'm just going to give the formulas rather than do derivations. Then 26.3 is Kirchoff's rules, which is the way that it's the simplest, most direct way to solve a circuit, which I'm going to show you one way, sort of the higgledy-piggledy way of a very simple circuit. And then after that, if time allows, I will show you the robust way of doing it with Kirchhoff's rules. But there are other rules. If you've had circuit theory or something like that, you probably know about the nodal method and the loop method and stuff like that. Anyways, any of those ways you're welcome to use. Just be advised, like I said, I'm just teaching one way. So use that or use whatever you want. It's just I may or may not be able to help you with the other way. Your book also talks about EMF in series and in parallel and tells you how to charge a battery. It also tells you quite nicely how to jump your car. So that's a good thing everybody should know because there's various dangers in jumping a car. Uh, After that, it's section 26.5, which is RC circuits, resistors and capacitors in series. There's a circuit for charging a capacitor. Then there's a similar circuit once you have a capacitor charged that'll be discharged. And we'll just give you those equations. I normally solve the differential equation to get it, but I've done that in enough videos on my YouTube channel. Really, what's more important is just the results. So, and that's what you'll have access to. Then in section 26.6, it talks about electric hazards and safety. And then 26.7 teaches you how to take a galvanometer and make an ammeter or a voltmeter out of it, which is what I love, but I might be skipping because we just don't have as much time as I'd like. So anybody have any questions for that before we get started? Okay, well, what I'm going to do is I'm going to go ahead and show my screen, and I'm going to basically, I'm not even going to take time to show you much about the equations that they introduce before they introduce them. I'll often just post them as the part of a solution to a problem. So let's go ahead and get started. I'm going to do so, as I said, by first sharing my screen. So here's my iPad screen. Should come up any minute now. Okay, so I've mentioned this before, but basically what we do when we're treating a battery to treat it like a more real life battery is we assume it has a perfect EMF source inside of it. And then somewhere between the perfect EMF source and its terminal versus the terminal of the battery, that is, there's a internal resistance that in fact can grow over time, and that actually is good enough to account for the fact that the voltage drops across the terminals when you actually connect it to a load like a light bulb or something like that. And what your book is telling us is that there's an equation that's really straightforward for finding the terminal voltage of a battery, specifically V terminal is equal to the electromotive force minus I times R, where R is the internal resistance. So you can see, obviously, if you really want to know the terminal velocity, excuse me, terminal velocity, if you really want to know the terminal voltage, you have to put it under a load so you can see, uh, find out what the current is. Or if they tell you that they want a specific terminal voltage and they tell you the EMF, the ideal EMF, then you can use that to decide what current would be necessary. I was saying this is internal resistance. They also are using that same notation we covered early on when we first started covering voltage. And for instance, we could have this battery that this diagram corresponds to could be basically this. And then if you imagine it as an actual battery, it'd probably look something like this. And this would be a little terminal up here. And this point would be A, and this point would be B. And then you'd say V terminal is equal to VB minus VA, which we'd also call VBA. So that's some more terminology for you that we used, and just reminding you what it was from this chapter on voltage. So with this one, what we say is we've got a 75 ohm resistor connected to the terminals of a battery. We're supposed to, whose EMF is 12 volts and whose internal resistance is 0.60 ohms. And A, we want to know what is the current in the circuit, and B, what is the terminal voltage, and C, how much power is dissipated by each resistor. So I'm going to go ahead and draw the diagram here. What we really have is essentially a battery like this. The EMF is 12.0 volts. Since it's right next to a battery symbol, we really don't have to put units on that. You know exactly what the units are. I'm also going to put 0.60 next to that with no units. That should make perfect sense as well. I'm going to now run from here. And obviously, since this is the long side of the battery, that's the positive side, and this the negative side. So this would be like the positive side of the battery. It's going to be connected to another resistance. And in this case, this resistance is 75.0 ohms. And I didn't have to put that ohm there, so I'm going to take it right off again. All right, so what we see, and we haven't really made this argument yet, but I think you've had enough experience in lab to know that these two resistors are technically in series, therefore their total resistance is just the sum of the two. So what I'm going to do is use V equals IR, which is Ohm's law, of course. So that's another thing I put up here, V equals IR. And in this case, the R is the 0.6 plus the 75, and the V is the 12.0 volts. So I'll say 12.0 volts is equal to I times 75.0 ohms plus 0.60 ohms. Therefore, I is going to be, all I got to do is take 12 and divide it by 75.6. So that's 12 divided by 75.6 gives me 0.15. Now notice when you add these together, you still only get one decimal place. So that's 3 sig figs, and then 3 sig figs into 12.0. So I really only have 3 sig figs. I'm going to say this is 0.158. And I'll carry 2 extra sig figs if I need it. And that's 73. And this would be amps. So you're looking at about 159 milliamps is what the current is. So we've got that. That's part of what they asked for in part A is what is the current in the circuit. Actually, that's the whole thing they asked for in part A. So I'll put a part A there. Now in part B, they want to say, what is the terminal voltage? So they want to know really how much voltage difference there is between, let's say, this spot and this spot. And anywhere really up to anywhere from here to there is fine for this side. And anywhere from, actually from here to here is okay on this side. Okay. So what I can do is I can realize that if I go from here, which is essentially on the zero side of the battery, that voltage could in principle be 0. So I could put a little bubble there and just write 0 volts. And then as I walk this way, it's going to jump up to 12 volts. So right here, if I put a little bubble, it would be 12 volts right there. Now, this right here is going to be a drop of the current times 0.6. So this one would be really the 12 minus I times R. Okay, so that's what my terminal voltage is, which, by the way, notice is exactly this formula here. Okay, so yes, we can go ahead and use the formula, or we can think it out this way. The main thing is that's what we're doing. We're doing the terminal voltage. So for part B, the terminal voltage is supposed to be the EMF minus I times the internal resistance. Well, the EMF we know is 12.0 volts. And then minus the current we know is 0.158, and then 2 extra sig figs makes the 7 and the 3 amps. And then the internal resistance is 0.60 ohms. So we're going to get 12 minus, I'm going to use the answer that I just had, and I'm going to multiply that by 0.6. And this is 3 sig figs times 2 sig figs. So I'm actually only going to get 2 sig figs after I multiply the answer. So pretty much I just get 2 decimal places. So this will be 11.90, but then I'm subtracting that from 12. So that literally brings me back to 1 decimal place. So the answer is going to be, whoa, didn't expect that. The answer is going to be 11.9 and 0.5 is my 2 extra digits. And that's the terminal voltage for this battery. Anybody have any questions on that one? So that's part B. Now, part C, they want to know about the power dissipated in each of the resistors. So what I want to remind you is the formulas for power are P equals IV, but that's also I squared R, but that's also V squared over R. And from that, we should be able to figure out what we want. So for instance, we're wanting to calculate the actual power, and what we were given was the resistance, and then we had to calculate the current. So I think the I squared R would be just as good a thing to use as any other version. So I'm going to do that. So the power in the internal resistance will be called P sub little r, and it's going to be I squared times little r, which is going to be 0.158. Don't forget the 2 extra sig fig or non-sig figs, 7.3. That's going to be squared, and then I'm going to multiply that by 0.60, which is going to make, of course, whatever this result turns out to be, it only have 2 sig figs. So I'm going to take 0.15873. I'm going to square that and then multiply that by 0.6. And that is 0.01512. 2 extra digits there. So that's how many watts that the internal resistance dissipates. And that literally just means that basically that little resistor that you have in the circuit, which in this case is a made up one inside the battery, but basically there's enough heat being put off by it that that's what's happening. It almost means nothing here, but in some sense, if you think and that sort of is what the internal resistance is, and if you think you really could accurately model that as a resistance inside, then it might be reminiscent of how hot the battery gets. But that's speculating at this point. But it is the kind of experiment you could do to find out if you're curious. So now let's do the other one. Oops. Let's do the power dissipated by the big 75 ohm resistor. So in this case, it's still going to be I squared R, but it's going to be 0.158 two extra digits, 73 amps squared times 0.60 ohms. Don't know why I left the units off last time, but 0.15873 squared times oops, I said 0.6. What goober I am. Hopefully y'all caught that. We're now supposed to be doing the 75.0 ohm resistor, and that ohm was supposed to be in there. Okay, so I'm going to say times 75. Now this one will actually have 3 sig figs, so that'll be nice. And with this one, we actually get an answer of 1.88. That's all the sig figs are supposed to have, so I'm going to add 2 more in case we need anything. So that'd be a 9.6. And that's watts, and that's P sub big R for the 75 ohm resistor. And you see that's basically on the order of 2 watts. Remember, a watt is a joule per second, and remember, a joule is about as much energy as it takes to lift a red, delicious apple, a really good, succulent, juicy one, from the height of the ground to the height of a kitchen table. So this is basically enough energy every second to lift 2 of those. So any questions on that? Or at least one nice one and one putrid one that's only, 88% the weight of the other. All right, so now what we're going to use is I'm going to make use of the relationships we found for the equivalent resistance. So what we did find, I will write in the solution as part of the equation we're going to use. But this says, example 26.2, consider the 2 identical light bulbs shown in each figure below. Which configuration produces the most light or produces more light? Basically, it's 2. You can look at this like headlights of a car. That's really what they're leaning for or leaning towards. So you can say that's like a 12-volt battery. And you can either put the 2 light bulbs, which are headlights, in parallel, or you can put them in series. And I will tell you that though the power is not how much light comes out, it's a little closer when you're using compact fluorescent lights. But when you're using a regular incandescent light bulb, I've heard it estimated that maybe as little as 1% of the power in a 100-watt light bulb is actually going to visible light. The other 99% going to basically infrared radiation heating up your house. So either way, though, whatever that factor is that you have to multiply by the wattage that's marked on the bulb to get the wattage of the actual light that comes out, that factor is pretty much going to stay. So that's what we're going to do. We're going to try to calculate the power in the 2 configurations. And once we have the power in the 2 configurations, the one with the highest power for the 2 light bulbs total will be the way that's preferred. And of course, we'll probably figure out that that's exactly the way they do wire such headlights. So let's get started. Hopefully everybody understands the setup. Here's our solution. So what I need to remind everybody of is that we've got P is equal to IV is equal to I squared R is equal to V squared over R. That's kind of handy. We also know that R equivalent in series is R1 plus R2 plus dot dot dot, and 1 over R equivalent in parallel is equal to 1 over R1 plus 1 over R2 plus dot dot dot. And we also know Ohm's law, which says V is equal to IR. So those are some expressions we're going to look at. So let's first off take circuit A. So in circuit A, basically what we're going to have is R equivalent. 1 over R equivalent is going to be 1 over R plus 1 over R, which obviously is equal to 2 over R. Therefore, R equivalent equals R over 2. Now, let me explain something about that equation. So the fact that the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the resistances in it tells us that the equivalent resistance is always smaller than the smallest resistor in the circuit. So that's something that's kind of neat. And as you can tell here, in fact, the smallest resistor in the circuit is R, and we got R over 2, so that's smaller. Okay. So that's kind of nice. And because of that, that means that we can now use V equals IR to figure out how much current leaves the battery. So using V equals IR, we get V0 is equal to I times R over 2. That's because we can literally replace those two parallel resistor light bulbs by one resistor whose resistance is R over 2. And when we do that, what we can see is we'll get I is actually equal to 2V0 over R. Okay. So now we have basically the current going through the circuit. That means this current right here is 2V0 over R. And then, of course, what we know is when this gets to this junction, when this gets to this junction right here, the current has a choice. It can go to the right or it can keep going straight. Now, these two resistances are identical, so that means there's no reason for one to have more than the other, so they're both going to be equal. That means what we're going to have coming out is half as much current because each one's going to get the current well, if you add the two currents that each of them have, which you could both call I1, you'd say I1 plus I1 is equal to 2V0 over R. Clearly, I1 plus I1 is 2I1. 2I1 is equal to 2V0 over R tells us I1 is equal to V0 over R. So now I can see that the current through each of these capacitors, or excuse me, through these resistors is going to be V0 over R. So if I want to know the power for one bulb, I could use P equals IV. That would require me to know the voltage across it times the current. Or I could use P equals I squared R. That requires me to know the current and the resistance in it. Or I could use P equals V squared over R. That means I have to know the voltage across it. And then I have to divide that by the R, which I do know. So any of those will work. I'm going to go with P equals I squared R. So P1 equals I squared R. That's going to become V0 over R squared times R, and that's just for one bulb. But what you see is you get V0 squared over R squared times R, which equals just V0 squared over R. Now P2 is going to be the same. And now we can say P total for part A now is equal to 2V0 squared over R, like that. Now we can do the same thing for part B. Oops, I forgot I used capital B. So now I use the same thing for part B. Now in part B, I'm going to say R equivalent is equal to R plus R, which equals 2R. Now, using V equals IR, I can solve for I by realizing that V0 is equal to I times 2R. Therefore, I is going to equal V0 over 2R. So I now got the current, and this current is V0 over 2R. Notice it's 4 times smaller than the current coming out of the battery in part A. So that's a good indicator that we're probably going to find less power here, but we don't necessarily know yet. Now that I have the I and I know that this is a singular wire that leaves the positive terminal of the battery and goes all the way back to the negative terminal of the battery with no alternate paths, this current is the current for both bulbs. So I'm going to use I squared R again, and I'll say P1 is equal to I squared R. So what we know is I squared is V0 over 2R. That's going to be squared. And then I got to multiply that by R. That's going to give me 1/4 V0 squared over R squared times R, which equals 1/4 V0 squared over R. Now P2 is going to be identical, so that's going to be 1/4 V0 squared over R. So that means P total, and this is for part B, is equal to 1/4 plus 1/4, which is 1/2 V0 squared over R. And you can see that this is in fact 4 times smaller than the other one. So what we can conclude is it seems that about 4 times, I should probably not write an X here, 4 times as much light is produced in A as, well, that about 4 times as much light is produced in A as is, or than is, I'll say as is, in B. So yeah, I would imagine, and it is in fact the case that when you run the wires to your headlights of your car, that they are in fact run in parallel. That also has the advantage that since light bulbs, at least the incandescent ones, literally go out by a piece of metal melting through usually, then that means it opens the circuit. And if you had an open circuit in configuration B, that means no current would be able to flow at all and both lights wouldn't work. Whereas if you had it in configuration A, what would ultimately happen is the one battery or the one light bulb that died will, of course, go black, but being an open circuit, it's not going to allow any current to go through it. So all the current can go straight through the one light bulb instead of the other. So the other light bulb will be working and be a little bit brighter. Any questions on that? All right, so notice in that one I did give you guys your equations for the equivalent resistances in series and parallel. So I just want to remind you that, and notice that it looks exactly like the formulas that we use for capacitances, but they're opposite. So capacitance, when they're in series, their equivalent capacitance is given by its reciprocal is equal to the sum of the reciprocals. But when they're in parallel, just their sum gives you the equivalent. So just keep that in mind, and that'll normally keep you straight. So let's turn to example 26.3. As you notice, I'm labeling these so that you'll know what problem they're like in your book, but they are a little different. This one says find the equivalent resistance of the configuration below and use that to determine the current supplied by the battery. Find the current through and the voltage drop across each resistor. And I drew the diagram. Oh, there it is. Good. I drew it in the wrong place. Yeah, that's what happened. I was like, what happened to my figure? Okay, I'm going to try to get smart and make a copy of this. It says copy. And I'm going to say paste. So there's my circuit. Okay. And in fact, I could actually just erase this one. I think I will, because obviously it's not going to that problem. All right, so this is a really simple one. You can look in my YouTube channel for other videos where I reduce a nasty configuration of resistors. Do that, configuration and resistors. Just do a search for that and you'll find a ton of them. But what I'm going to do is take an easier one and I made it a little bit harder than the one the book had. But I'm going to go ahead and do everything the book does. So I want to actually figure out what the equivalent resistance of this is, and then I'm going to go ahead and figure out what the voltage drop across each one is, as well as what the current through each one is. So when I look at this, immediately I try to look for any two or more resistors that apply to the formulas that we have for equivalent resistances. Now you can sort of see that the 400 and 100 might have, but they're really on opposite sides of the battery. So in principle, they're going to be the same, but not yet. Okay. But the 500 and the 600 are definitely in parallel. So what I'm going to do is I'm going to say, for starters solution, and I'm going to put our formulas down so we know V is equal to IR, that's Ohm's law. 1 over R equivalent in parallel is equal to 1 over R1 plus 1 over R2 plus dot, dot, dot. And then R equivalent in series is equal to R1 plus R2 plus dot, 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 like that. So I'm going to start off with I56. Oh, excuse me. It's supposed to be R56. With R56, which means the equivalent for the 500 and 600 ohm resistors. Notice again, I did leave the units off. I didn't really have to put them on there because they're next to a resistor drawing, so clearly it's resistance. With this one, it's going to be 1 over 500 plus 1 over 600. As you can probably tell, the 500 nor the 600 are the least common denominators, but in fact, 3000 is. Uh, because if you multiply 600 times, yeah, I think this would be 3000. Let's double check. I just came up with that on the fly. I hadn't worked this before, so let's see. 3000 divided by 500, clearly, and 3000 divided by 600. Clearly. All right, good deal. So I just want to make sure you know how I am about my arithmetic. So what I'm going to do is I'm going to multiply 1 over 500 by 6 over 6. I'm going to multiply 1 over 600 by 5 over 5. And what's going to happen is I'm going to get 6 over 3000. And then when I multiply 1 over 600 by 5 over 5, I'm going to get 5 over 3000. And 6 plus 5 is 11. So that's 11 over 3000, which means that R56 is really 11 divided by 3000. And that happens to be 0.0036667, gearing my classic 2 extra sig figs. Wait a second here. What happened? Yeah, that should be fine, but 3000. Oh, I did it upside down. No wonder. Stupid me. Well, at least I'm catching them tonight. I've made a couple mistakes already, but yeah, it should be 3000 divided by 11 from your crackhead instructor. So, whoa, Nelly. So, R56 is actually about 272.73 ohms. So that's the equivalent resistance of the 500 and 600. So if you're looking at it now, we've got a 400, we've got a 273, and then we've got, whoa, Nelly, a 100. So that's really all we've got left. In fact, they're all in series, so this is super easy. We can now say R equivalent because this will be one resistor that represents all of them. That's going to be equal to 400 plus 100 plus 272.73. I'm going to assume the 400, 500, 600, 100 are all 3 sig figs. Either way, though, you're going to get that's 500 plus 2 be 772 equals 772.73 ohms. So that's the equivalent resistance. So now what we can say is we basically have the equivalent of a 12.0 volt battery in series with only a 772.73 ohm resistor, or excuse me, resistor. I'm going to go ahead and say this is equal to R equivalent and box that off as part of the answer. Even though I think I just asked, I said find the equivalent resistance of the configuration below and use that to determine the current supplied by the battery. So that's sort of the whole point of equivalent resistance. Once you find the equivalent resistance, then you obviously have a case where V equals IR automatically applies. So now that we do that, I'm going to say 12 point, whoa, I'm going to put it back in the color we were using. I'm going to say V equals IR gives me 12.0 volts is equal to I times, oops, times 772.73 ohms, again, extra digits, so that I is equal to 12 divided by 772.73, and that gives me a very small 15 amp current, about 0.01529 amps. And that 2 and that 9 are not significant. So these are both part A answers. Any questions on that? Now they want us to find the current through each one. Now, what we've immediately noticed is that the way the original circuit was, if 15.529 milliamps comes out of the 12-volt battery, then that 15.529 milliamps is going to go through the 400. It's also going to go through the through the 100, and not only that, it's going to split to make up what goes through the 500 and the 600. So we can use all that information to make sense of exactly what it is, and we can solve for the various currents. So right off the start, I know that well, I'm going to write it back in purple. Right from the start, I know that I total is equal to I4, which means for the 400 ohm resistor, and that's equal to I1, which means for the 100 ohm resistor, and that's well, I'll go ahead and write it as milliamps. That's 15.529 milliamps. So we now have I1 and I4, and of course I total. Now we can use, since we have I1 and I4, we can find out what V1 and V4 are. Using Ohm's law, we can say, well, actually, using Ohm's law, I'm going to say V equals IR. So I can basically conclude that V4 is equal to 15.529 milliamps times 400 ohms. And that gives me since I'm multiplying by milli, that actually gives me milli. So this is 6,211 6.6, and that would technically be millivolts, which obviously we don't want. So it's going to be 6.2116 volts. So that's again 2 extra digits. So we now know that V4 is equal to 6.2116 volts. We can do the same thing for V1. That was V4. For V1, we're going to get V1 is equal to 15.529 milliamps. And again, I'm just doing this with milliamps so you'll know that, you know, the milli can just be carried through. And we pretty much only do this with electronics. But if you divide, for instance, by a milli, that would be a kilo. If you multiply by a milli, that's going to be a milli, that sort of thing. So now we're going to do times 100 ohms because this is for the 100 ohm resistor. So I'm going to say 15.529 times 100, obviously, is going to be 1,552.9. And of course, that comes out to millivolts, which is no good for anyone. Also has 2 extra figures that aren't good. So this is going to be 1.5529 volts. That's what V1 is. So V1 is equal to 1.5529 volts. So what that tells us, for instance, is I could put this bubble right here, and that actually extends to this point as well. I can put the 0 volts right here, but that also extends all the way up to there. But now that I know the V100 is 1.55, then I know that this right here would only be about 1.55 volts because it was 0 after it. And obviously, the current was going that way, so that would be a voltage drop from there to there. But this also happens to be the voltage at this point as well as the voltage at this point. Not only that, the V400 being 6.21, I can take 12 minus 6.2116, and that's going to give me 5.7884. So right here, this is going to be 5.7884 volts. Now that's basically what it is right after the 400, but that is also what it has to be here and what it has to be here. Again, ignoring the slight resistance of the wires. But what we've managed to do now is we now see that the voltage on the left-hand side of the 5-volt battery, or excuse me, of the 500 ohm resistor is 5.7884, and the voltage on the right side of the 500 ohm resistor is 1.55. So that should, if we subtract those two, that should give me V5, and which is also equal to V6 since they're in parallel. So I'm going to subtract 5.7884 minus 1.5529, and that gives me 4.2355. So suspect V5 equals V6 equals 4.2355. Now I say suspect, but that's got to be right. So we'll keep that in mind. But now I'm going to work it the more traditional way. What I wanted to show you guys is now that I have a certain amount of current, specifically 15.529 milliamps coming out of that 400 ohm resistor, it comes to this junction right here, and some's got to go up, but some's got to go down too. And in fact, what we know is that more current will go through the smaller resistor than goes through the bigger resistor. Okay, so what I got to do is implement that. So what I know, for instance, to implement that, I know that the 500 and the 600 ohm resistor are in parallel. Therefore, I know V500 is equal to, well, actually, I've been calling it V5, so I really shouldn't put those there. So V5 is equal to V6. We know that. We also know from Ohm's law that V5 would be I5 times 500, and V6 would be I6 times 600. So that's something neat that we know. But something else that we know is I5 and I6, they both came from the total current, which was 15.529 milliamps. So these two must add to give me 0.015529 amps, like that. So I'm going to call this equation 1. I'm going to call this equation 2. And from equation 1, I'm going to say that I5, which is the smaller resistance, therefore it should be the larger current, is actually equal to 600 over 500 times I6. And of course, that's just 6/5, or 1.2 basically, times I6. Now, just to double check, 6 divided by 5 is 1.2, as I said. So now what I can do is I can say plug this into 2, and what I get now is I5. I'm going to write 1.2 I6 plus I6 is equal to 0.015529 amps, like that. So this is, in fact, this is in fact giving me that 2.2 times I6 is equal to 0.015529 amps. Again, the 2 and the 9 are not significant figures. So I6 is going to equal, it's going to be equal to 0.015529 divided by 2.2. And that gives me 0.00705. Now I'm put 2 extra sig figs on there. It's 8.6. Or 2 extra figures on there. That's 8.6 amps. So it's about 7 milliamps basically. And now that tells us that V6 should equal 0.007. Well, let's do it in a whole nother line, because I see that's just getting too crowded. So now I can do V6. Dang it. Now I can do V6 is equal to 0.0070586 amps times 600 ohms, and that's times 600, and that gives me 4.2352. So not only is it right, but it's right to 1 extra digit beyond the significant digits. So I now have I6, and I now have V6. And again, we know that V6 has to be equal to V4, but we should calculate it anyways, and we should calculate I4, I5. And I meant V6 is supposed to be equal to V5. Sorry about that. Oops, that's supposed to be a 6. And it's supposed to be purple. Okay, there it is. All right, so now what we do is we realize that
I5, can't tell you how angry that makes me. What we realize is that I5 is equal to 1.2 times I6. So that's equal to 0.007058 times 1.2. That gives me 0.00847. So that's my 3 sig figs, and then 0.3 amps. And that means V5 is equal to 0.0084703 amps times 500 ohms. And this is 4.2352. And that's volts is equal to V5, which again is another check. You can see again it gets the right answer as we had predicted, even to an extra digit beyond the number of sig figs we're supposed to have. And I'll go ahead and write I5 here. I5 is equal to 8.4703 milliamps. Any questions on that one?
It looks like Micah slipped out and is back in, so let me let them in. No questions on that one? So this is sort of a higgledy-piggledy way of solving a circuit. It's sort of convoluted, but it's fun. I mean, I consider it a nice problem-solving skill. And then the fact that it leaves you a back door to check things like, does the voltage in any one complete circle add up to to zero when you put negatives as drops and put positives for increases in voltage and stuff like that, and use conservation of charge, of course, for the junctions so that the currents add up properly. And it's just, I don't know, it's kind of fun. But like I said, there's a much more tried and true way that work every time, and it just makes it a little bit more formal. So we'll show you that as well. Let's start off now with, it turns out when you, one way of trying to engineer a product is you could just run basically a wire uh, from your battery of your car to, for instance, a fan. And a fan is just a little electric motor, and it can be represented by a little bit of resistance, maybe some back EMF or something crazy like that. But the main thing is really just resistance is what you care about. And that resistance is going to tie the current down such that V equals IR. So if you're using a 12-volt battery, you've got 12 volts at your disposal. If you only have the resistance of the actual fan in there, then I is just 12 volts divided by the resistance of the fan. Uh, but you might want multiple settings. So one way you could set multiple settings is that would be the high. And if you want it lower, you could slip another resistor in series with the actual motor. And if you do that, that will make the net resistance higher, and therefore the net current is lower. And that's a typical way you could engineer a fan to have more than one speed. And that's what they're asking here. They're saying estimate the resistor that must be put in series with a fan motor to make it run, that's supposed to be run off or run on 2.0 amps rather than the usual 5.0 amps supplied by the 12-volt battery. What power rating should the resistor have? So that's a good question, because not only is it asking you to, how to design something, it's also saying, okay, let's make sure not only that we do this, but that we spec the right resistance, because if we get the right resistor but not the right power dissipation, then it's going to burn up lickety split. So that would be a pain. All right. So
what we're going to do first is we're going to try to see exactly what kind of resistance the motor has, specifically by realizing that probably the only thing uh, in series with the 12-volt battery and the motor is basically the wire and the motor itself. So what we're going to get is resistance that accounts for the resistance of the wire plus the resistance of the motor. Probably most of that would just be the resistance of the motor, but we'll see. So solution, well, is what we need here is Ohm's law, V equals IR. We also need power, which is IV, which equals I squared R, which equals V squared over R. And we also need R equivalent in series is equal to R1 plus R2 plus dot dot dot, like that. Okay. And by the way, you are supposed to have 3 dots. It's called an ellipsis. So don't make more than 3 dots. Just make three. So if you guys possessive compulsive professors like me, they won't be turds to you. Anyways, let's carry on. What I'm going to do now is realize I have according to Ohm's law, I have a 12.0 volt electric fan, or excuse me, car battery that's connected to an electric fan running a current that we found was 2.0, or excuse me, 5.0 amps, because that's how much it normally runs on, times the resistance. And in this case, it's the resistance of fan fan plus wires. It's always going to be the fan plus the wires, but the main thing is probably the fan's the biggest one and what you care about. So with this in mind, I can now figure out the resistance of the fan is going to be 12 divided by 5. 5 goes into 12 two times, and there's 2 left over. That's 2/5. That's 2.4. So this resistance would be 2.40 ohms. I'll double check that because I am known to making careless mistakes. So 12 divided by 5 is 2.4. That was right. I'm very impressed with myself. All right. Hey, I'm trying to entertain you guys. All right. So now I've got that resistance. Now, what's going to happen is basically we're going to have this 12-volt battery, and it's running into a motor that has a resistance of 2.40 ohms. And then now what we're going to try to do is slip another resistor in here, R equals question mark. But now what we want is the current to just be 2.0 amps. So now what we're going to do is we're going to say solve for little r, but we're going to use Ohm's law. That's going to say 12.0 volts is equal to, in this case, 2.0 amps times, now what we have is 2.40 ohms. That's one extra sig fig there, plus lowercase r, and that's got to be multiplied to get the 12. So what I have now is 12.0 volts is equal to 4.80 volts plus R, plus, excuse me, plus 2.0 amps times R. Okay, so now what I've got to do is subtract the 4.8 from the 12.0. So 12 minus 4.8 is equal to 7.2. And that's equal to 2.0 amps times R. So R is going to have to be 3.6 or 3.501, I think, or 3.505, I think. 7.2 divided by 2 is 3.6. No, I was right the first time. 3.6 with extra sig fig there. So that's the resistance we're going to have to put in there. Now what we got to figure out is how much power should it be able to dissipate. So we know that the current going through it is going to be 2 amps, and we know that power P is equal to IV R is equal to I squared R. I think we should do I squared R because I have I and R. So this is going to be 2.0 amps, which is going to be squared times 3.60 ohms. So 4 times 3.60 would be 12, 14.4. So that's 14.4, which is one extra sig fig watts. So I'd say at least 15, 18 watts if we could find it. So need at the least uh but 20 would be better. Now remember, basically, when you start motors and stuff like that, there's a little period for them to get hotter and hotter. So when they get hotter, the resistance gets higher, which means when they first start up, the resistance is going to be low, so you're going to draw a buttload of current. So you don't necessarily want to design for just 2 amps. You want to design for a little bit bigger than 2 amps. In fact, if the cost wasn't prohibitive, I would jump even as far as 25 watts. But anybody have any questions on that one? All right. Well, it looks like I am going to be able to get to this one. And this one says solve the following circuit for the three currents shown. Note, students are not usually given a diagram with the current directions chosen. They usually have to do that themselves. I just want to let you know, it's when you're doing a multiple choice, it's reasonable that you at least label what leg is going to have what current. But you don't necessarily have to put the arrows on it. What I want you guys to understand is that there should be some thought into which direction you think the individual currents are going, just so that you can get some feel for how the circuits behave over time by saying, oh, in this case I thought this, so I ended up thinking this one would be going to the left and that would be going to the right, and I was right, so that makes me feel good, blah blah blah. That kind of stuff you should do. So you should do that every time, but notice that if you're wrong, it's not a big deal. It's just going to come out negative when you do the math. And you just keep using that negative until you finish using all those equations. And then later you can maybe think about why it was negative instead of positive. But to do all this, I want to point out that we need Kirchhoff's rules. So here's our solution. First off, Kirchhoff's rules, or Kirchhoff's, depending on how you want to pronounce it. I have no idea what the correct pronunciation is, what Mr. Kirchhoff would have said himself. But the main thing is we need to know him. He also has a set of rules that we use in astronomy that tell us why certain types of spectra coming from stars and nebulas and whatnot. Same Kirchhoff, so that's kind of interesting. But first one is Kirchhoff's loop rule. So the KLR says the sum of all the voltage drops, which by the way will be negative, and increases, which obviously will be positive, in a closed loop is equal to 0. So in other words, if you add up all the voltage changes going in any closed loop, so you start at one place on the circuit, you take any path you want, doesn't matter whatsoever, but return to that one spot again, okay, then all the voltage increases and decreases should add up to give you 0. That's Kirchhoff's loop rule. Then there's Kirchhoff's junction rule, the KJR, and in this one it says the sum of all the currents entering a junction is equal. Oh, I think I put an extra loop in that. To the sum of all the currents leaving the junction. Now, that first one's conservation of energy. The second one's just basically conservation of charge. You know, if you got 7,000 coulombs of charge coming in, and then you've got three currents coming out, then the sum of those three currents better be 7,000 coulombs per second, which obviously is an amp. So the same thing happens if it's, 7,000 coming in through three different outlets or through three different wires into the junction. The sum of the three coming in has to be equal to the sum of the three coming out, or the sum of the 12 coming out, or whatever. So that's just the conservation of charge. Uh, what I'm going to do now is I'm going to apply Kirchoff's loop rule to this very circuit. And what I'm going to do is compute the voltage drops and increases in a closed loop. But what you need to understand is when you're actually crossing a battery, if you go from the short bar of the battery to the long one, that's a voltage increase. If you go from the long bar to the short one, that's a voltage decrease. Also, if you are going across a resistor in the direction that you chose the current to be pointing in, then the resistor has to be a voltage drop. Otherwise, if you go across it the other way, it's got to be a voltage increase. So that's what we're going to do now using all that information. And first off, I think I'm going to do the bottom loop. I think that's what I want to do. No, I'm going to do the upper loop first. So let's look at the upper loop. So what I'm going to do is I'm going to imagine starting from right here and just going this way. Notice in so doing, I'm going the same way as current I1 and the same way as current I2. So let's go ahead and write our solutions. So as I start in there, the first thing I run into is the 30 ohm resistor. So that's going to be, since I'm going the direction of current, that's going to be minus 30.0 times I1. And now I go around, I run into the 50-volt battery. The 50-volt battery, I'm crossing going from the short leg to the long leg, so that should be plus 50. Notice everything's coming out in units of volts here because the 30 ohms times I is giving you volts as well. And then I'm going through the 1 ohm resistor again in the direction of the current, so that's minus 1.00 times I3, and then minus 40.0 times I3. And now I'm back to where I started, so I'll just say equals 0. And this was top loop. Okay, now I'm going to combine like terms a little bit here. And basically what I'm going to say is I'm going to say this is 50.0 minus 30.0 I1 minus 41.0 I3 is equal to 0, and I'm going to call that equation 1. Does everybody follow what we did there? Anybody have any questions? All right, so now what I'm going to choose is the outer loop. So let's go outer loop. And your choice of loops is somewhat irrelevant. But if you choose it where one is common to both equations, there's some neat tricks you can use. So let's do this outer loop. I'm going to start at the same spot. I'm going to start right here, go all the way around like this, and come around this way. Notice this time I'll be going the opposite direction of current I2, so you'll see some of the weird behavior. So the outer loop starting, the first thing I want to run into is negative 30.0 I1. And then notice now I get all the way around to here. This is where I'm going the opposite direction of the current. So the resistance is a voltage increase. So I'm going to say plus 20.0 I2. And then plus 1.00 I2. And then I'm going from the long leg of the battery to the short leg. Therefore, I'm looking at the battery as a voltage decrease. So that's minus 90.0 volts. I don't need to mark the volts there. And now I'm back to where I started, so I can write that as equals 0. Again, I can clean this up a little bit by combining like terms. This time I'm going to say 21.0 I2 minus 30.0 I1 minus 90.0 is equal to 0, and I'm going to call that equation 2. So what I now notice that I can do is I have an I1 in equation 1 and equation 2. So if I solve equation 1 for I3 and solve equation 2 for I2, then I can replace I2 and I3 with something about I1 in a junction equation, which brings me to Kirchoff's junction rule, which I'm going to take this one. Of course, you could have done this one. There's always one extra node, by the way, or one extra junction. But this one, we see we've got I3 coming in and I2 and I1 coming out. So I have another equation that I3 is equal to I1 plus I2, and that's Kirchhoff's junction rule. And I'm going to call that equation 3. Okay, so if I solve this one for I3, what I'll get is I3 is equal to, now what's going to happen is I'm going to pull the 30 I1 to the other side. It's going to become positive. That's 30.0 I1. And then I'm going to pull the 50 over there too, and that's going to become minus 50. And then I got to divide by a negative 41. And that is what I3 is. I can make this a little simpler by taking 50 and dividing it by 41. In other words, I'm going to take the negative and reverse the order. So by taking the negative away from the bottom, I can call it 50 minus 30 I1. But then I'll take 50 and divide it by 41. And that gives me 1.2195. That's 1.2195 minus now 30 divided by 41. That gives me 0.73. So I can say 0.73171. I1 is that one. So what I have now is I3 is equal to 1.2195. I ran out of space because of my obsessive compulsiveness with the digits. So 0.73171 I1. So this is what I'm going to call equation 1 prime. Now I'm going to do the same thing for I2. I'm going to solve for I2. And this is going to give me I2 is equal to, I'll pull the 90 to the other side. That'll become, instead of minus 90, that'll become positive 90. So that's 90.0. Now I'll pull the 30 I1 over there. So that'll be plus 30.0 I1. And now I'm going to divide all that by 21.0. This one I might be able to fit a little better. I'll take 90 and divide it by 21. This is the way I like to do it. This is going to be 4.2857 plus, now I'm going to do 30 divided by 21, which I've already done. No, I divided by 41 earlier. So this is 1.4286. And that's I1 as well. So this is going to be equation 2 prime. Now all I have to do is plug these into equation 3. So now I've got I3 is equal to I1 plus I2. That's going to give me 1.2195 minus 0.73171 I1 is equal to I1 plus 4.2857 plus 1.4286 I1. So you can see we've got a lot of I1s. It looks to me like we should pull them all on the right-hand side. So what I'm going to do is I'm going to subtract 4.2857 and I'm going to add 0.73171 I1 to both sides. Okay, so when I do that, I'm going to get 1.2195 plus, excuse me, minus 4, I had put plus 4.2857. That gives me negative 3.0662. And when I pull all the other i's over to the right-hand side, I got 1.4286 plus 1 plus 0.73171. That gives me 3.16031 I1. So I1 we can figure out is obviously going to be negative, but it's going to be this gives me 0.97022 amps for I1. And then I just put that in for my expression for I2 and my expression for I3, and I'll be done. I don't think I made any mistakes here, but you guys can check it. I know our time is up, so I'll probably finish this at least in the notes and then continue it, but you guys are free to go. I'll wait here for the last person to leave in case anybody has any questions, but other than that, have a great Thanksgiving. Don't forget to get your face-to-face test and your online test done. Those of you who had missed online test 2, there's 2 people. I opened that back up again for y'all to have until the 3rd to get done as well. So you have your face-to-face test, your online test, and then those of you who missed the online test 2, you have also that to do all by December 3rd. So have a great, safe Thanksgiving break. Have fun, and thanks for coming.
Happy Thanksgiving.
Thank you, Carter. All right, I'm going to go ahead and try to plug this in real quick while I'm still on video. Micah, do you have a question, or are you just going to hang out?
Yeah, I was just wondering if I was able to take the test after work again, like I did last time or before work.
Yeah, you got the same person
It might
rostering?
she's taking leave off. I
Okay.
have and that's for my late night job. That's why it was late. During the day I work for the government. So I might have my supervisor from there.
Yeah,
Um,
I just have to go through that process again and send them the
again with a
question.
different
So
person.
yeah,
Yeah,
that's the only
totally.
downside. But yeah, if you can get to the actually, I've got one person that's not going to be able to do it till the 5th or 6th. So if
Mhm.
that helps you any, I can allow you that much time. But you have
Okay.
assessments
I
there. But if you can't
I
get
would
that,
definitely I would if it's not her, which I mean I have to see exactly how that date range when she actually does get back, if she gets back, because she's like taking the Thanksgiving off, but if she gets back, what the third is Tuesday, right?
yes.
Yeah, so I think she gets back that Monday, which I mean that might work out anyway. So, but if it doesn't, then I will let you know that it'll be a different guy, and I'll give you his contact information, and he'll reach out for
Okay,
the
that's cool.
exchange. Okay,
That sounds
sounds
good.
good. Yep.
Thanks, Micah.
Thanks for
Have
the
a good
info.
one.
You too.
Bye
Happy
bye.
Thanksgiving.
Happy Thanksgiving. All right, I've got I2. Now I'm working on I3. I3 we got was 1.2195 minus 0.73171 times I1, which is negative 0.97022 amps. And this should give me 0.73171. Notice that's a minus times a negative, so that's going to give us a positive. So times 0.97022. That is 0.7099, which will be added to 1.2195, and that gives me 1.9294 amps is equal to I3. We should make sure that these in fact add up to meet the requirements for equation 3. So I'm going to check I1 plus I2, negative 0.97022 plus I2 would be 2.8996, gives me 1.9294, which is exactly what I3 is. That works. Probably wouldn't hurt to throw it in one of the other equations too, just to see. Let's try. I'll try the 50. I'm looking at equation 150 minus 30 times, this time it's a negative 0.97022 minus 41 times I3, which is 1.9294, and that should all give me 0, and I got 0.0012, so that's good. So yeah, I have complete confidence that this is almost certainly correct. Thank you, everybody. Have a good one, and that's about it. Bye bye.